In 1542, a Polish churchman lay dying in his bed. On a nearby scrap of paper, he wrote the following lines. The shortness of life, the dullness of the senses, the numbness of indifference and unprofitable occupations allow us to know but very little. And again, swift oblivion, the embezzler of knowledge and the enemy of memory, shakes out of the mind in the course of time even what we knew. The story goes that in his very last days, he was handed a book which he had been working on for decades. Reports differ on whether he was pleased to see it or even whether he recognized it. He'd been refusing to publish it for some decades, afraid that it would make people angry. The book was called On the Revolution of the Heavenly Spheres, and the dying Polish churchman, Mikołaj Kopernik, is better known today as Copernicus. So, today's about the Copernican Revolution. It's really hard to think of a topic that's more central in the history of science, or to pick a better moment for kind of the initiation of modern science. Copernicus was famous for presenting what's called the heliocentric model of the solar system, that is, with the sun in the center rather than the Earth. Other people had this thought before, but Copernicus is perhaps most famous for having inspired the work of people like Galileo and Kepler and Newton, who we'll talk about next week and subsequent weeks, who present us with pretty much the modern conception of how the solar system works. So, in a chapter of Bala that I didn't ask you to read, he asks the following question. Could there have been an ancient Greek Copernicus? So, to keep with our theme of asking meta questions about the sort of narrative of the scientific revolution, I'd like to spend a little bit of time talking about this. This question is motivated by the traditional narrative about the scientific revolution, which is that it's a sort of simple rediscovery of the ancient Greek work in Renaissance Europe and sort of the revival of humanism. So if your picture of the history of science is something like this, the chart, the infamous chart, you can see why it would seem like there totally could have been, maybe not an ancient Greek, but a Hellenistic Copernicus. So if you believe the chart, which I don't recommend, it looks like, the Renaissance and the scientific revolution pick up essentially where the Hellenistic world left off almost 1,000 years earlier. So, and it's true that other people had the idea of a heliocentric solar system. So this guy, Heraclides, is actually cited by Copernicus himself. So Copernicus writes down the names of a few ancient Greek or Hellenistic authors who had proposed this that he was aware of. So Copernicus himself knows he's not the first person to suggest that the Earth goes around the sun. This guy suggested, it's not clear that he actually had a heliocentric model of the solar system, but he did have a model in which the Earth spins. So the stars make a kind of 24-hour revolution apparently around us, and Heraclides suggested that it's not the stars that are moving, but the Earth, which is already got the kind of very radical implication of the Copernican model of the solar system, which is that we are spinning around at unimaginable speeds. It already sort of, if you believe this, you already sort of believe that your senses are lying to you in some profound way. So my senses are screaming at me that I'm standing still right now, that the Earth is standing still, that my apartment is fixed in one location and the sun is going past. But as far back as, Heraclides, people have been proposing that actually we're moving while the stars stay still, at least. Copernicus's main kind of foil, his main competition, as it were, for models of the solar system is probably Ptolemy. So Ptolemy lived from about 100 to 170 CE, and he lived and worked around Alexandria, which is where the Library of Alexandria was. He lived under the Roman Empire and probably was either Greek or Egyptian. We're not quite sure. So the Library of Alexandria is still a hot spot for learning at this point, although under the Romans it had started a kind of slow decline that would take another 100 years or so before it petered right out. So Ptolemy gave us this book, the Almagest. The Almagest is probably the most famous textbook of astronomy throughout history. It was the standard textbook throughout the Hellenistic world, the Byzantine Empire, the Islamic caliphates, and once it had been translated into Latin from Arabic, it became once again the standard textbook in Europe. So this is the system of astronomy for like 1200 years or something. So Ptolemy's system, I mean, it looks roughly like this, and he's got a geocentric model. So the Earth is almost in the center of the solar system. You can see it's offset a little bit. To get the numbers to work out right, he had to move the Earth just away from the very middle. But everything moves in circles, perfect circles, which is an idea that he picks up from Aristotle, who picked it up from a bunch of other people, that the circle is the most perfect shape. And given that the heavens are made out of what he calls quintessence, which is the fifth element, and are all orderly and perfect, the planets and stars must be moving in these perfect circular shapes. Now, Aristotle hadn't actually tried to work out the math of how to predict where the planets would appear in the sky. So it was pretty easy for him to go, yeah, circles, good. Ptolemy actually built a predictive model. So he's not just giving you this like image, he's actually got a set of equations to work out where the planets are going to appear in the sky. And to get that math to work out, he had to make some adjustments. So one annoying thing that the planets do, if you're an astronomer, is what's called retrograde motion. So over a bunch of observations, this is sort of Mars doing its retrograde thing relative to the fixed stars. So the planets are moving relative to the stars. The stars, of course, are moving across the sky. But what you see is that the planets slow down and then reverse and then go back in the direction that they were heading in the first place. Retrograde motion. So that's hard to account for if the planets are just moving in very simple circles. So Ptolemy's got this construction called the epicycle. The epicycle, if you can see this little circle on the big circle. So Ptolemy's system has a bunch of little circles going around the big circle in order to account for things like retrograde motion. He had to build a bunch of these into his system to get the numbers to work out properly. And you can also see that he's moved the Earth off the center of the solar system a little bit. So the very center is the center, and then the equant is the sort of opposite point of the Earth, which is displaced from the middle. Okay, so Ptolemy's system, it's the system that Western astronomers are working for a really, really long time. I don't want to give you the impression that Ptolemy's system was unchanged over those 1200 years. The basic structure that Ptolemy lays down is unchanged. However, people are making more and more careful observations and fine-tuning the details. So the numbers that you plug in, or sometimes they added epicycles to like get observations to match the model better and better over those 1200 years. But Ptolemy lays the kind of basic structure in which these fine-tunings take place over more than a millennium, and right up to the time of Copernicus. So here's a picture of the Copernican system. Copernicus writes on the revolution of the celestial spheres, and he puts the sun in the center of everything. He's still using perfect circles. So in some sense, he's a good Aristotelian, right? He still thinks that the planets move in perfect circles. It's not till we get to Kepler that we'll see somebody move away from that basic model. And he still needs epicycles to make the numbers work out. So you can see the moon is on a kind of double epicycle thing here. So still perfect circles, still epicycles. It's not super clear that his predictions were even any better than the most up-to-date versions of Ptolemy, but Copernicus really hated the equant because it moved the Earth out of like the proper center of things. So the whole system is rotating around just kind of an empty point in space, and Copernicus manages to get at least the sun in the center of the known universe. And of course, in retrospect, we know that he's way more correct than Ptolemy, because he gets the basic position of the sun and the Earth and the planets correct. A couple other small advantages. Copernicus can explain why, when you look in the sky, Venus and Mercury are always pretty close to the sun. So whenever you observe Venus and Mercury, they're never like on the complete opposite side of the sky as the sun. And Ptolemy's system did have that as a kind of consequence, but for Ptolemy, it's sort of a big coincidence, whereas for Copernicus, he's got a really nice explanation for why that's so. It's because Mercury and Venus are closer to the sun than we are. Okay. So back to Bala's question. So, okay, that's a very short version of the one of the biggest revolutions in the human thought, but that's what you get. But let's try to do some context here. So back to Bala's question, could there have been an ancient Greek Copernicus? So could we have gone straight from Ptolemy to Copernicus? And Bala thinks no. There was a couple of things, actually a number of things, that Copernicus had access to that Ptolemy didn't. So for one thing, he had way better math. And that's what I'm going to take up just very briefly here. So Copernicus has got, in the 1200 years between Ptolemy and himself, much more advanced mathematics, and particularly stuff like trigonometry, which is super useful for like figuring out how things are moving around circles. So to see where his much more impressive math came from, it's helpful to look at classical India. Okay, so just to get a flavor of this was by no means the only institution of higher learning in classical India, but Nelanda University is perhaps one of the earliest big institutions of higher learning. It's founded in something like the 5th century CE. Counts vary of how big it was, but the estimates put it at around something like 10,000 students and 2,000 teachers. So pretty big for the 5th century. And they needed something like 200 entire villages producing food to feed all these people. Okay, so really, really big, really long lasting. At Nelanda University, you could get a whole bunch of different kinds of education. It was primarily founded, I believe, as a Buddhist school, but you could learn about Hindu philosophy, medicine, math, logic, natural science from all over. So people came from really far and wide to Nelanda University to learn from it. So they had access to the Mesopotamian astronomical tradition, which had made it to India centuries before, possibly as early as the 4th century BCE. So the Mesopotamian knowledge has been in India for quite some time now. Shortly before Nelanda is established, the ancient Greek astronomical texts, so the Greek and Hellenic traditions, had made it to India as well. And those were studied as a kind of interesting starting point for further development of mathematics and astronomy. Okay. One of the most famous teachers at Nelanda University, we think he was a teacher at Nelanda University, but certainly he's one of the most famous, or he's like the ancient Indian astronomer mathematician, was Aryabhata. I mean, there was lots of them, but he was like the guy. I'll just run through a few of his contributions. This guy's got amazingly prolific, but one of the things he suggests is, in fact, that the Earth is spinning and that the stars stay still. So he had that, and he worked through a bunch of the arguments for and against that position. So arguments like, okay, if the Earth's spinning round and round, why don't we fly off? And he had some kind of ancient version of inertia, not exactly like our notion of inertia, but something like it. So he's made this stunning conceptual leap already that, in fact, we're spinning round and round. He also did stuff like calculate the size of the Earth. So if you remember from last time, Eratosthenes had done this to within about 5 to 10% error. Aryabhata calculates 39,968 kilometers or thereabouts for the size of the Earth, which is off by about 2%. So this guy knows he's able to calculate the size of the Earth within 2% margin of error. It's pretty good. And he's not just an astronomer, he's also making big leaps in mathematics. So he does this like he writes a textbook, which is canonical for centuries. He does an amazing synthesis of the available work and also makes advances of his own. So he's one of the first people to use the sine function from trigonometry. Although precursors to trigonometry can be found all over the place, his sine function is recognizably a sine function. Okay, so Aryabhata, one of the people early at the Nelanda University. Other people like Brahmagupta made incredible advances in trigonometry. For example, how to, if you've got a trig table, so if you tells you what the value of a sine or trigonometric function is, so you got a bunch of calculated figures, he gives you a technique for finding intermediate figures on the trigonometry table, which is convenient if you don't have like an infinitely long trig table. He also provides some of the first clear rules for dealing with 0 as a number. So 0 as a placeholder has been around for a really long time, but Brahmagupta is one of the first people to give systematic rules for dealing with it as a number in its own right, which is of course part of the mature numeral system that we've all inherited. Okay, and just to mention one more person, I don't think any of these people actually looked like this, but whatever. Okay, so Bhaskara II developed a version of differential calculus like hundreds of years before it's developed in Europe. He worked out how to apply differential calculus to trigonometric functions, and frankly, at this point in the development of math, I don't really follow what's going on. The math is too complex for me to actually understand what he's achieving. So I take it on the good authority of smarter people than myself that people like Bhaskara and Brahmagupta and Aryabhata are making big advances in the kind of sophisticated science or sophisticated mathematics that underwrite doing really good astronomy. And they're also doing good astronomy. Okay. And of course, as I mentioned, they're working with a vastly improved number system compared to at least what Europeans were working with. So from the Indian subcontinent, you get the kind of like original version of this. It's developed over centuries. By the time of Brahmagupta, we've got this sort of very familiar 0 to 9 with decimals, with a place system. So just like exactly the kind of numbers that most people are familiar with working with. So this gets developed over centuries and then gets passed through, a bunch of this advanced math gets passed through either the Mongolian Empire or through the Islamic caliphates, comes into Europe during the Renaissance, where Copernicus did his work, sort of late Renaissance or early scientific revolution. So Copernicus is working with a much sharper set of mathematical tools than Ptolemy was. Okay. So he's got much more advanced math to deal with the problem of trying to construct a heliocentric model of the solar system. Now, that's not the only thing that changed in Europe since Ptolemy's time. But the difference from Copernicus's perspective doesn't sort of appear yet in other ways. So you might be surprised to hear that Copernicus's new heliocentric model of the solar system doesn't really make much of a splash. Some astronomy nerds thought it was cool, including people in the Catholic Church. They were like, cool, that's neat. Don't say it's a real thing. Say it's just a fun way of doing calculations. But, good work, Copernicus. He's dead by this point. But they're like, good work, Copernicus. So what makes it revolutionary in the scientific revolution, and what makes Copernicus a kind of world-shaking figure for modern science, is the way it's received. And the way it's received is sort of radically changed by the philosophical shifts that were going on in Europe at the time. So in the other video for this week, I'm going to talk about some of the ways in which their picture of nature itself was changing. And with that changed picture, Copernicus's model becomes something truly revolutionary. Okay, thanks.